I now have the pleasure of introducing our keynote speaker for this morning. To kick off today's learning, we're excited to begin with that keynote speaker who really sets the foundation for the conversations we'll be having throughout the day. As specialty producers, we're all thinking about how to build operations that are not only productive, but also resilient, economically, environmentally, and over the long term. Our keynote this morning will explore how intentionally designed farm systems modeled after natural ecosystems can help strengthen specialty crop operations while staying grounded in real-world production and business decisions. Our keynote speaker is Dr. Kelsey Murray, a biomedical and environmental engineer, educator, and founder of Aqua Acre Market, a South Dakota-based specialty crop operation and learning hub. Dr. Murray's work sits in the intersection of regenerative production, local food systems, and agricultural education. Through both hands-on farming and teaching, she focuses on practical ecological principles such as diversity, nutrient cycling, redundancy, and place-based adaption, and how those principles can be applied in ways that support both environmental integrity and economic stability. She brings a unique perspective that connects the production system, business models, and long-term resilience, offering actionable strategies that specialty crop producers can realistically apply within their own operations. We're excited to have her here to help frame today's discussions and inspire our learning ahead. Please join me in welcoming our keynote speaker, Dr. Kelsey Murray.
Thank you for that wonderful introduction. I'm really excited to be here today. So let's get started. I have an off-the-wall question to get us going. You can kind of just think of the answer in your head. What do things like medical adhesives, wind turbines, antibacterial surfaces, what do these have in common? The answer is that all three of these examples that I gave are all ideas that we borrowed from nature. So I'm going to start with the first one here, this adhesive medical tape, and what inspired it. Geckos. Okay, so we're going to have a little lesson on geckos this morning. So did you know that geckos don't climb walls because their feet are sticky? They don't use any suction to adhere to the wall. Instead, their little feet are covered in millions of microscopic hair-like structures that increase surface contact. So each hair is tiny, and on its own it doesn't do anything. But together, all of these little hairs work together in such a way that they're strong enough to hold the entire body weight of a gecko. Okay, so even if they're upside down on your vacation rental ceiling, right, they've got these really cool foot pads. And here's the really elegant part about gecko feet, is that they can turn this adhesion on and off really, really simply, just by adjusting the angle of their toes. No residue, no energy cost, no waste. And so once scientists realized that geckos weren't sticking because of some sort of secretion, but because of the structure of their feet, it changed a question that we ask entirely. So instead of asking, what can we make, stickier, the question then becomes, how can we design surfaces that behave in the same way as gecko feet? And so that insight really led to these gecko-inspired dry adhesives. So they're materials that can grip smooth surfaces, they can release on demand, and they can be reused over and over again. And so nature inspired that design. Next on my list, I've got humpback whales. So if you look at the humpback whale's fins, they have these knobby edges, and those knobby edges really help the whales maneuver through very turbulent water. And they do this very effectively. And so we've used that same, design of a whale's fin in order to make wind turbines. So we kind of add that little bumpy layer, and that improves wind turbine performance and stability in really unpredictable winds. The last example I have up here is shark skin, where, unlike whale skin that can be full of barnacles and kind of, gross looking, shark skin stays really remarkably clean. And that is because of the surface texture of that shark skin. It makes it really hard for bacteria to colonize and settle on that skin. And so we've taken what we learned from the shark skin and we've designed surfaces, say in hospitals or things like that, that can be antibacterial and resist contamination without relying on any disinfectants. So in each of these three cases, humans didn't invent anything new. We noticed that nature had already solved a problem and we learned from it. And that idea has a name. We call that biomimicry. Okay, so now here's where it gets bigger than a few really clever inventions. Life on Earth has existed for about 3.8 billion years. And over that time, more than 99% of all species that have ever lived on this planet are extinct. Not because they were weak or because there was some flaw in the organism. It's because they couldn't adapt when conditions changed. But the species that remain, including us, we're the survivors. And as biomimicry pioneer Janine Benyus puts it, they represent something called natural genius. They didn't survive because they're the strongest or most efficient. They survived because their systems were designed to handle change. So when we look at, many of the systems we built, especially in agriculture, we often design for efficiency under stable conditions. But as we all know, ecosystems aren't stable. They're very dynamic. And when systems that are optimized only for efficiency, they tend to break down when there's change. So instead of asking, how can we control nature better, a more useful question might be, how does nature design systems that survive uncertainty? And so that question really is the foundation of regenerative design. Okay, so, nature's been dealing with instability forever, for a long time, millions of years. And long before we had fertilizers and irrigation schedules and crop insurance and market forecasts, ecosystems already knew how to survive uncertainty. They learned how to persist through droughts and floods and other disturbances. And yet a lot of modern agriculture is still designed around optimizing individual pieces. We might optimize fertilizer rates or plant density or feed conversion rates, but we don't often stop to ask whether the system we've developed, whether that system can handle stress. And so today I just want to talk a little bit about what happens when we flip that thinking. So when I'm talking about regenerative design today, I'm not going to be talking about a checklist of practices. There will be plenty of talks in the rest of the day that will give you actual checklists of practices you can implement. But what I want to talk about today is really how these systems are built. So this design way of thinking really asks whether a system can recover from stress, adapt to that change, function over time. And so instead of chasing these short-term efficiency goals, we're really going to focus on relationships and how energy and nutrients and information move through systems. Okay, so in agriculture, we really want to design farms that behave more like natural ecosystems. So when you look closely at how natural ecosystems remain stable over long periods of time, we find these same patterns that show up again and again. You'll see them in forests, you'll see them in wetlands, oceans, and grasslands, and you'll see them really in any system that's designed to handle stress. And so today I'm going to focus on three of these principles: diversity, redundancy, and nutrient cycling. And to highlight each of these examples, I'm going to use aquaponics as a working example. One of the challenges that we face when talking about regenerative design is that it can feel really abstract. right? Ecosystems are so complex, and most of the time we don't get to see all of these relationships at work. And so that's why I'm choosing to use aquaponics as a core example today. Not because it's the answer for every farm. Certainly, I'm not encouraging all of you to jump into the aquaponics business. But really, we're using it as a way to explain how aquaponics can make ecosystem design visible for all of us. So in an aquaponics system, the relationships between the organisms and the nutrients and management decisions are very immediate. If something is out of balance, you're going to see it right away in that system. And so aquaponics really then becomes a really great model for how regenerative design actually works. And aquaponics is, close to my heart because it's how I became an accidental farmer. I'm a biomedical engineer by nature. I've studied the relationships between human health and the environment, and I accidentally became a farmer through aquaponics. And aquaponics is the foundation of my company, Aqua Acre Market. I do want to spend just a minute talking about how I got into aquaponics. I was a college professor at the local technical college, Western Dakota Tech. And kind of the weird thing about the program that I ran, which was environmental engineering, is that we didn't really fit in the school. There's kind of two main tracks at Western Dakota Tech. You can go into healthcare-related fields or trades-related fields. And then there was us in environmental engineering. So we didn't really fit anywhere. So I was looking for ways for our students to become more integrated in the school. So we were looking for projects that could be cross-curricular, where students could work together on projects, but apply the skills that they need to be successful in their careers. So we came up with this idea of aquaponics, and this is a really great idea for us. Aquaponics obviously fits perfectly into environmental engineering. We can use it as a system that teaches all kinds of environmental principles. But through this project, we were able to collaborate with so many other departments. We had plumbers that would design the pump systems. We had electricians that could design the control systems. We had construction trades that could actually build the systems for us. We had nursing students who could teach about the nutritional value of the products grown in these aquaponic systems. And so, this is how I became an accidental farmer, was we just needed a tool to help teach students the skills they needed to be successful in their careers, and this was the tool we chose. So if you don't know what aquaponics is, it's a food production system that has been in practice for thousands of years. Okay, this is not anything new. The cool thing about aquaponics is it combines aquatic organisms, which we have over here with the fish in that little tank, and plants, which we kind of have on that far side there. They're combined into this single integrated system. So when the aquatic organisms produce waste, their ammonia and waste gets converted into nutrients for the plants. So these systems have these amazing bacteria that can do all of the work for us to make that harmful fish waste into plant food. The really cool symbiotic relationship here means that the fish are helping the plants, but the plants are also helping the fish. So the plants work to clean the water and make sure that everything is, functioning. So in these systems, there's no soil involved. The system really is entirely dependent on the biological relationships here and the nutrient cycling in the system. So what makes aquaponics really useful isn't necessarily that it's high tech, although it can be. It's that it's an example of biomimicry, right? This is exactly how nature does it. And so that's why I'm going to use aquaponics today as the framework for my talk. And it's not a recommendation for every operation, but this is just a really clear model for how your regenerative design can work. So now we're going to look at the principles that make a system like this possible. Sorry, I'm getting over a cold here. Okay. So I'm going to talk about 3 principles today, and the first one is diversity. And diversity shows up in aquaponics. So at its core, aquaponics only works because it relies on this diversity. You've got the aquatic organisms, the plants, the bacteria, and they're all interacting at the same time. And so even within these subgroups, diversity matters. We want to have different aquatic species that can tolerate different temperatures or different water conditions. We want to have different plants in the system that use nutrients differently and pull them out of the system at different rates. We also need a diversity in the microbial community. There's different microbes that specialize in different parts of the nitrogen cycle. And so having that diversity in an aquaponic system really spreads the risk. If one thing would fail in the system, the idea is that the rest of the system could manage that. Okay, so when aquaponic systems are simplified too far, which often happens where you're just growing one crop, using one species of fish, that's when aquaponics becomes fragile, right? We can have these small disruptions that turn into big problems. But if we build diversity into these systems from the start, the system really can absorb that change without constant intervention. So one of my favorite examples of diversity in aquaponics style growing, it doesn't come from a lab or a greenhouse. It comes from rice paddies in China. So for thousands of years, farmers in China have grown rice in these flooded fields alongside fish and crustaceans and oftentimes ducks. The plants and the animals and the microbes and the ducks, they all work together in the system. So in a traditional rice, duck, fish system, we don't usually have a single pond or a single field. We're designing these systems as a series of these connected ponds and connected paddies. And I don't know if you can kind of see that. If you kind of look into the distance of this picture, you can see there's little separate ponds as you move down. So in the system, the waste moves, but it doesn't really disappear. We're just redirecting it. Nothing in the system is treated as waste. So what's really cool is that, each downstream pond is going to receive partially processed nutrients. So they're not going to just get the raw waste. And therefore, each of these ponds serves as sort of a biological filter. The upstream ponds tend to be more nutrient rich, and downstream ponds tend to have much lower nutrient loads. We will incorporate different plants or algae or organisms in every pond at each stage of the process. And so this prevents nutrient overload and really spreads that productivity across the whole system. Okay, so when you look at these systems from above, this is an aerial view of a rice paddy. What stands out is that, again, they're not built as the single unit. They're designed as this series of interconnected ponds and paddies. And every pond supports a different function. So the rice paddies are where, the primary productivity occurs, right? That's the main goal of the system, is to produce the rice. But the fish ponds are great for nutrient conversion and pest control. The fish eat the bugs that could potentially, interfere with your crop. We have settling ponds built into the system, so that can help sediment capture. We have vegetated ponds that really help with water clarification. And so if one of these ponds becomes stressed, the nutrients are really going to become buffered before they reach that next stage. And so downstream systems aren't immediately harmed because one of these tiny little ponds fails, and recovery really can happen quickly without total system failure. So again, this protects the water quality, the crops, the aquatic life, the environment, all simultaneously. So by the time the water exits the system, nutrients in the effluent are lower, the sediment is settled, and the biological oxygen demand has really been reduced. And so this really is regenerative design at a landscape scale, right? This is not just a field scale. So instead of, treating the waste, the system spreads the work out of processing it. So what's really important here is that there's no one single organism that's doing all of the work. Productivity is really coming from these interactions and not from the inputs themselves. So these systems, historically, if you look at the data, they tend to be way more productive and way more stable than rice monoculture cropping. They also require far fewer chemicals, far fewer pesticides. And so this is really diversity as design. What makes this system work, apart from its diversity, is that we have multiple organisms that are performing overlapping functions. And so that is going to lead us to our second principle, which is, oh no, we're out of order here. We'll talk a little bit about our second principle, which is redundancy, in a minute. Okay, so diversity. We all know that that's important, right? And as specialty producers, diversity can look like a lot of different things. Maybe diversity looks like planting multiple crops instead of monocultures. And one of my favorite examples of this would be the Three Sisters method of growing. So if you aren't familiar with Three Sisters, it's an indigenous growing system that was developed by a lot of native nations in North America. And it plants corns, beans, and squash together. And that is because each of these crops is going to do something to support the other crops in the system. So corn, that'll grow tall and it'll act as a natural trellis for the beans. The beans can fix nitrogen from the air and enrich the soil for all of these plants to grow. Squash is really cool in that it spreads along the ground, and so that'll shade the soil and hold in moisture and suppress weeds. And so together, these three sisters can really create the self-supporting, resilient system that improves soil health, reduces the inputs, and produces more food than we can if we grow each of these crops individually. And so this is an early and very powerful example of this design practice, where we're basing it on relationships rather than how we can control the growth of each individual species. As specialty crop producers, we can also kind of think of diversity in non-biological ways too. Maybe we're thinking about diversity in who our buyers are. I don't want to have just one single buyer for the lettuce that I grow in the aquaponics system, because what happens when that buyer decides they no longer want our product, right? We need to have multiple market channels in order to give us that stability and that resilience. Maybe, those multiple market channels might look like offering both fresh and value-added products. Maybe it's involving a combination of CSA and wholesale and direct sales. Maybe it's adding different revenue streams instead of just the one income source. And so this is what I've done with Aqua Acre Market, where we've added things like education and agrotourism and other services so that we aren't dependent on just one cog in the wheel. And so research really, really consistently shows that diversified farms are just far more resilient to economic and environmental change. One thing that I want to point out is that diversity doesn't necessarily maximize profit in the best year. So what I mean by that is we're not aiming for just, more. What we want to aim for is reducing the chance of failure in your worst year. Okay. So when we simplify agricultural systems too far, here's my example of a cornfield, we really lose that buffer. So if I compare that cornfield that is experiencing drought to a neighboring plot of land that is, let's say it's prairie in South Dakota, we can see that because that prairie has diversity, that even though both systems are experiencing drought, the drought in the prairie is still allowing for a really active and resilient ecosystem. Okay, so I do kind of want to spend a minute really looking at the prairie ecosystem here in South Dakota. Prairies are, often described as simple, sometimes like boring landscapes. Ask anyone who drove, from Sioux Falls or wherever to here, right? It's a pretty boring drive. But prairies are actually some of the most complex and resilient ecosystems on the planet. We've got these really deep-rooted plants that can pull nutrients and water from far below the surface. We've got shallow-rooted plants that can respond quickly when it rains. Some species will grow early in the season, some will peak in the heat of summer, others are going to hang on later into the fall. And really having that diversity spreads risk. When conditions change, and they always do, the system doesn't fail all at once. That diversity, again, spreads the risk. Prairies are also really cool in that they're designed for disturbance. Fire is really a common occurrence and part of the natural ecosystem cycle in prairies. Drought, those are all things that the ecosystem, quote unquote, expects. The prairie can survive not because it tries to avoid this disturbance, but because it was built to respond to it. So there's no single species in the prairie that really holds it together. The stability of prairies come from the interactions. If one species struggles, the system is going to adjust. Okay, so that's going to bring us to our next principle, which is redundancy. So I do want to circle back to aquaponics and talk a little bit about, how diversity isn't the only thing that makes an aquaponic system successful. It's making sure that we have multiple organisms in that system that can perform overlapping functions. Okay, so when people hear the word redundancy, it often sounds like inefficiency, right? I'm an engineer, and in my field, redundancy is usually something we try to eliminate. We're taught to streamline and optimize and remove anything that might look unnecessary. But ecosystems actually do the exact opposite of that. In natural systems, redundancy really is the key. You've got multiple organisms that can perform these similar functions, often in slightly different ways. And so that overlap is really what helps insulate the system from failure. So in aquaponics, redundancy is non-negotiable. Growers are going to build backup aeration systems and redundant pumps and multiple filtration stages. And, every experienced aquaponics operator is going to have the story where redundancy prevented a catastrophic system failure. And I do want to tell a little bit, one example of this where we thought we had redundancy in our aquaponics system. Turns out we didn't, and we lost thousands of fish. Okay, so what happened was we built this system at the school. We were growing fish for game fish and parks to release into stock ponds for fishing. We had the system obviously plugged into the main electrical system in the school. We also had our system plugged into our backup generator system in the school. Okay, so all the outlets are a different color. They're red when you're plugged into the emergency backup system. So we're thought, okay, we're golden. If the power goes out, which it often does in the middle of winter in South Dakota, we'll be fine. Like the generators will kick on. Turns out that whoever installed our electrical system put the wrong outlet cover on the outlet. So when we thought that we were plugged in to the emergency backup system, we weren't. So that is an example of where we thought we had redundancy. We didn't. And I came into school to hundreds, thousands of floating fish. And that was like one of the hardest days of my career because, using these fish in a teaching way, they kind of became special to us. They're like our little pets. They would come up like little puppies and when you would feed them. And so that was a rough day. Okay, so we need to have redundancy in a lot of different ways. So my example was electrical redundancy. But we could look at redundancy in terms of biological, functional, infrastructure, market, labor, and knowledge redundancy. So we start at the top here. Biological redundancy really gives us this ability to keep our farms functioning if something in the system fails. So we're not relying on one crop, one variety, one planting window. We're going to have multiple crop species with overlapping functions. So I'll just give you like a couple of really simple, straightforward examples. Maybe you're growing spinach, but that spinach bolts. So we also have backup crops of lettuce or kale that can still help us carry that season. Maybe we want to buy multiple varieties of the same crop that have different genetic tolerances built into them. Maybe we want to have heat tolerant and cold tolerant and fast turn varieties all together in the same system. Maybe for our biological redundancy, we want to stagger the plantings so that one weather event doesn't wipe out the entire harvest. So the outcome from having the redundancy, the biological redundancy, is that we have reduced crop loss from weather or pests or disease. And so the system really bends to those disturbances rather than breaking. Functional redundancy is also important. So there's always more than one way to do a critical job on the farm. So, that could be related to things like nutrient supply or pollination or pest control. You should never depend on a single mechanism to achieve any of those goals. So some really good examples would be, let's focus on pollination. Obviously we want the beneficial insects on our farm. So, what can we do? Well, maybe we need to make habitat for those insects so that they have a place to thrive on our farm. Maybe that means adding in managed bees instead of nature's bees. Maybe that means mixing in some wind-pollinated crops and some self-fertile crops so that if one of these pollinator systems declines, the whole pollination system won't collapse. So this is really helpful too when one input becomes maybe too expensive for our farm. We can still operate the farm because we have redundancy in those systems. The third one I want to talk about here is infrastructure redundancy. So infrastructure failures can be catastrophic, as we know with my fish example, right? We didn't have the redundancy we thought, and we lost a lot of fish. So smart redundancy is going to look like, adding backup irrigation zones or backup water sources. Maybe we have redundant pumps or power operations in our system. Maybe we're planting separate crop blocks instead of planting one contiguous field. And so again, the outcome is that local failures, when we have this infrastructure redundancy, are going to stay local and they're not going to take down the whole system. Okay, market redundancy is a big one for all of us. Our income shouldn't hinge on a single buyer. Again, we need to incorporate direct to consumer and wholesale and institutional buyers. Maybe we want to focus on fresh sales and value-added products. Maybe we want seasonal offerings and year-round offerings. So again, markets will shift, but because we have that redundancy built in, they don't really become existential threats to our operation. Labor and knowledge redundancy is big here. The farm isn't person dependent. So if only one person knows how to do something, that's really introducing a lot of fragility into your farm. We want to make sure we have cross-trained staff, written SOPs for reference, using simple repeatable systems rather than these really highly specialized ones. A great example of this right now is my employee's last day at Aqua Acre Market is today. She's moving on to bigger and better things. And, we need to have that labor redundancy so that we can carry on our operation without her. Okay, redundancy is an important second principle, and that'll kind of lead us into our third principle, which is there is no waste in nature. So one of the biggest differences between natural systems and human design systems is how we handle waste. So in nature, there's really no such thing as trash. There's only leftovers. Every output from one organism becomes food or fuel or structure for something else. And so when waste builds up in nature, it's a signal that something's been broken, not something we need to manage with more inputs. So we think about a forest floor. Leaves fall and trees die, and animals leave waste everywhere. Yet the forest doesn't drown in that debris. And that's because we have decomposers, bacteria, fungi, insects that are constantly turning that waste back into nutrients. And so again, in this system, nothing is exported, nothing's ignored, everything stays in the system and stays in motion. And so that's going to bring us back to my example of aquaponics. Aquaponics is a really great example about that shows how there is no waste in nature. So we look at the nitrogen cycle. Fish are going to excrete ammonia. So that happens through their gills, through their pee and their poop. In an aquaponic system, we build up a ton of surface area. In that surface area live all of these tiny microbes, again, which is my specialty. I'm a biomedical engineer who loves microbes. And these microbes have really specialized functions. And there are some that can convert that ammonia into nitrites. And then there's other bacteria that convert those nitrites into nitrates. And so without those bacteria, what would happen? The waste in the system from the fish would build up to a point that it would become toxic to both the fish and the plants. But because we have this natural cycle and we're not wasting anything, the waste from the fish can get converted into this food for these plants, and the waste actually drives the system. So across specialty agriculture, we're really dealing with similar pressures, right? I'm going to just kind of wrap up what we're talking about, kind of show that regenerative design is not just a trend. This is something we should always have in the back of our mind as a high-level view of our operation. We're all, whether we grow indoors like I do or outdoors like presumably a lot of you do, we're going to have similar pressures, right? Maybe it's climate variability. Maybe it's rising input costs, labor shortages. That's a big one. Market volatility, maybe even down to like consumer confusion around labels or value of the products we grow. And so each of these challenges often gets treated as a separate problem, right? We're only going to figure out how to lower the input costs, but we're not going to look at all of these other factors in our system. And so from a systems perspective, that really is indicative, they're symptoms of the same thing as fragile design. So ecologists have shown for decades and decades that systems that are optimized purely for maximum efficiency tend to lose that resiliency. So if we strip out redundancy and diversity, those systems are really going to become more vulnerable to disturbance. So we really have to start changing our way of thinking. We have to put these practices of regenerative design into practice. We all know, hopefully, that diversity spreads risk and redundancy keeps failures from becoming catastrophic. And nutrient cycles keep the systems productive over time. So I want to go back to where we started with the gecko feet. Geckos they haven't survived because they're stronger than gravity, right? They survived because how they're designed. Those millions of tiny contact points build redundancy into the structure, right? You lose one, you don't lose the ability of the gecko to grasp the wall. It doesn't matter that there's thousands of hairs that are doing that same job. That's not an accident, right? That's design that's shaped by survival under challenging conditions. And that's really what regenerative design is about. We're not going to copy nature exactly, but what we need to do is step back and learn how nature builds systems that keep working when conditions change. Systems don't depend on perfection, right? Early on in my aquaponics career, we wanted to get the most perfect head of lettuce every time we grew it. And guess what? We learned quickly that that's never going to happen. What we did was making sure our systems didn't collapse when one piece of the system failed. Okay, when we learned that our redundancy wasn't actually redundancy, what did we do? We bought a backup generator in addition to the school's backup generator, so we had 3 levels of redundancy there. That way, if something happens, again, the power went out multiple times when I was working at the college, and our systems didn't collapse when the power went out. And again, it's because we had used these design principles. So remember that systems where nothing is wasted and everything stays connected are the most resilient systems. So for all of the specialty crop producers, I think the question really becomes, can we control every variable? And the answer clearly is we can't, right? So climates are always going to change. Markets are always going to shift. Inputs are always going to fluctuate. Labor is always going to stay tight. But the farms that last are not going to be the farms that are designed for that perfect high yield year. They're the ones that are designed like the gecko feet, where they keep holding on even when conditions aren't ideal. So with that, I'm going to wrap up my talk and leave some time for questions. Yeah.
So what type of plant do you grow in your aquaponics?
Okay, great question. So he's asking what type of plants we grow in our aquaponics. So I'm going to give you a couple of examples here. In the school system, we grew, like, you name it. So my research partner, Brian, who's the electrician in here, just decided he was going to get whatever seeds he could find, from wherever and toss them into the system and see what happens. Me, as a scientist who wants to study exactly the effect of every little thing in the system, my brain went blah, right? So in those original systems, we had varieties of lettuce and squash, and we even tried root vegetables, carrots and radishes and things like that. They don't go well in aquaponics. But we tried a little bit of everything. As we took aquaponics more into a commercial application rather than a teaching application, we've honed that a little bit. So at my shop downtown, we're still building our teaching farm, but ultimately we'll just have some basic lettuces, herbs, leafy greens, things like that. Tomatoes and strawberries are kind of our main crops. We are also working on this really cool project that I'm so proud of and so excited for, where we're building an indoor farm for Rapid City area schools. They serve 6,000 lunches a day. So that's just the lunches. And we want to be able to provide produce for free for the school system. So we're actually under construction this week in Alston's classroom. to put these systems together so that we can provide produce for the school lunches. So because of the USD regulations on what needs to be served at school, we have to have so many, dark green leafy products. We have to have tomatoes. And so we're going to adapt what we're growing in the system to match the nutrition guidelines that are mandated by the government.
I guess the follow-up question is, what type of fish are you raising?
That's a great question. So he's asking what type of fish we're growing in the system. We grow a little bit of everything. So if you're going to venture into aquaponics, always start with something cheap. So the first thing we bought was goldfish, right? Because if you lose a few goldfish, you won't cry as much as if you lose thousands of trout like we did. We have grown anything from tilapia, which is a great food fish that's really bland. So it's appealing to restaurants because they can season it to their recipes. Again, we've grown bluegill, tilapia, channel catfish. We've done freshwater shrimp. We even had a system that my students designed that incorporated chickens into the system, and we used the eggs and the waste to kind of feed back into the nutrient cycling. The fish are the crop that it's the slower crop in the system. It can take anywhere from 9 months to a year to get a fish from fry size to plate size. And so we really have to design the systems so that we're choosing the right crop of fish. And the vegetables can be changed out a little more frequently because their growth cycles are a little shorter. So we've done a whole variety of things. Like I said, we did a lot of pond stocking in the last couple of years for game fish and parks. Hopefully that answers your question. Okay.
Hang on, wait.
Sure.
You use multiple species of fish in the same tanks, or
Great question. So he's asking if we use multiple species of fish in the same tanks. And the answer to that is ideally. Some fish don't like it though, right? They want to eat the rest of the fish in the system. And so we tend not to mix, like, say, some species of fish that might compete with each other. You want to put fish together in such a way that they're acting kind of synergistically. Really, like our basic example is we put our koi and our goldfish together. Again, those aren't the food fish. They're kind of snazzy for the students to look at when they're like, oh, look, we grew these fish. When we started incorporating things like duckweed into the system, the fish would just eat that, right? Before the duckweed could really kind of help the system. So we have to make sure we're matching up species that aren't going to compete with each other, but that are going to work together. Yeah.
how big is your system?
Okay, so we've built a ton of systems. So we started off by building a system that was 10 feet by 10 feet. And if you design a system like that correctly, you can indefinitely feed a family of 4 for a whole year with all of your nutritional requirements met. The system up at my shop is going to be really small once that's built. But we've done much more scalable systems. A couple of years ago, we got to go to Costa Rica to build an aquaponics system. This was a really cool project in that, not only did they want to diversify the nature of the crops, but they really wanted aquaponics to be a point of community. And so this was a much bigger system where it was actually through a ministry that they were using to make sure that needy members of the community could get fed for free. So the scale of the system can be, I'm going to put it on my countertop in my kitchen and grow my herbs and, a few little lettuces and things. Or it can be like, we're trying to feed a community of 6,000 students or a community in Costa Rica. So it just depends. We've got all sizes.
So 6,000 students, how big is this going to be?
So we're starting, so let me back up a little bit. A couple of years ago, we started a pilot project at East Middle School. That system was more of in line of our 10 by 10 system. So it was something the teachers really used to get students engaged and excited about where their food came from. In this system that we're building in Alston's room, we have 4 different types of grow systems in there. We will probably be able to produce enough for maybe the high schools with just that system. The idea, though, is that we don't want the farm to only be at Central High School. We want to have these little independent farms in all of the school systems so kids can see where their food comes from. They can interact with that. They have pride in that. You should see how happy these kids are when they get their first strawberry off of the plant. And so the idea behind our aquaponics is that we don't want this big eyesore of a system just built somewhere on the edge of Rapid City. We really want these systems to be incorporated into the community, not only to provide food, but to provide the education around that food. Did that answer your question? Okay. Yeah.
I was wondering if you had to add like supplemental fertility to how many of the plants in there, if you monitor fertility and you monitor like pH.
Yeah, so he's asking a great question. Do we add supplements to the system? How are we monitoring the system? And so the really cool thing is aquaponics can be as complicated as you want it to be. China's been doing it for thousands of years without electrical control systems or pH monitoring. But we come from a technical world where we want to be able to tie the growing of the food into the science. So we do absolutely have water quality monitoring equipment in the systems. We've made it so that the real only input into the system is supplemental fish feed. What's really cool is you don't even necessarily have to buy fish food to make the systems functional. You can oftentimes grow plants to feed the fish. And so, again, that really closes that loop. Yeah. Good question. So the system that we did a lot of the studies on, again, I had access to great experts in solar energy and things like that. We could get it down to $1 a day in energy costs. Now, is that practical everywhere? No, because we had to put in an investment. Again, we're a school, so we're lucky that we could get, tens of thousands of dollars worth of solar panels. So that might not be as feasible and as practical in other settings. So $1 a day is what we got it down to, though. Yeah.
Was there any extra food safety considerations or regulation stuff that you had to jump through hoops to be able to do this stuff?
Great question. He's asking about food safety when it comes to aquaponics. Aquaponics is, so it kind of saw a rise in the 70s and then it kind of fell off again. And now I think it's kind of coming back in fashion. And unfortunately, regulations haven't really kept up with the times. So, I've reached out to SDSU Extension and asked, what food safety rules do we have to follow? And there really aren't, aside from what we have to follow in any farm, there aren't anything specific to the field of aquaponics, which is something that we're trying to work on a little bit. The biggest concern for food safety in aquaponics is when people touch the water with their dirty hands, right? Kids don't wash their hands after they go to the bathroom, and then they want to go in and put their hands in the water. And so that's where we could introduce some potential pathogens into the water. Some fish can be carriers of human pathogens in their guts. But again, we send our lettuces or whatever for food safety testing just to kind of monitor that. In terms of the fish, there is an aquaculture regulatory body in the state that you have to go through in order to import fish across state lines. And so there is kind of minor regulation when it comes to the systems, but I do think that that's something that needs to like catch up with the times. And so we're kind of pioneering this in South Dakota and hoping that we can establish that food safety framework. Yeah. Any other questions? You guys have some really great questions. I really, really appreciate you guys taking the time out of your morning to listen to me talk about one of my favorite topics, which is aquaponics. I will be here for the rest of the day, so feel free to connect with me, and I'm excited to hear a lot of your talks throughout the rest of the day. Thank you.